Good morning and welcome to Tech 293 for Thursday, February 18th. My intention is for you to watch this video on whichever day between February 18th and February 23rd you are not in the lab doing Lab 4. Obviously you can watch it whenever you want to, but on the day that you are in the lab, there will not be a video that you have to watch. So this is for the other day when you're not in the lab doing Lab 4. So this video is all about doing calculation problems with tensile testing data, using tensile testing data to solve problems and applications regarding tensile testing. So I'm going to divide this kind of into two sections. In the first part of this video, I've got some example problems on my slides that I'm going to go through, and a reminder that you have all those slides, so you have the answers to those as well. So you can follow along with the slides if you want. And we'll talk through how to do a bunch of different kinds of problems with tensile testing data. In the second part of this video today, we're going to talk through an example worksheet that you already have in your lab manual, and that is on page 37 and page 38 of your lab manual. So what I would really recommend you do is maybe watch the first part of this video and get a feel for how to do these tensile testing problems using all of the information that we've talked about in the previous week or so that we've been talking about tensile testing. And then after that, maybe pause this video in the middle of the video and then try to solve the problems on page 37 and page 38 of the lab manual, because those are very good problems that could show up, or something very similar to that could show up on the next quiz or on the next exam. I mean, there definitely will be stuff like this. I mean, I'm not giving anything away by saying that. There will be stuff like this on the next exam and probably the next quiz or so also. All right, so with that, let's start talking about how to apply the tensile testing concepts and the equations that we've talked about up till now, and apply those to start solving some application problems with tensile testing data. All right, let's get started and solve some tensile testing calculation problems. These first few slides are not really that important. Basically, what I want to say in these slides is that you've got three equations that we're going to manipulate. You've got the equation for stress. Stress equals force divided by area. The second equation you've got is strain. Strain equals the change in length divided by the original length. And the third equation you got is for the elastic modulus. The elastic modulus equals the change in stress divided by the change in strain, and it's applicable only in the elastic region. All right, so we're going to use those three equations and a little bit of manipulation, a little bit of algebra on those, and we're going to solve a bunch of different types of problems in these examples here. All right, so what we can do, don't get too, don't memorize this right here. In fact, I wouldn't recommend really memorizing anything here except those three equations. I would definitely have those three equations down by memory, but nothing else here you really have to memorize. So remember, there's two kind of types of problems I can ask you. I can say, here's the load. We know the load. Find the change in length, delta L. So we'd go about that by taking our load and then calculating the stress, and then using the relationship with the elastic modulus to find the strain. And then once we know the strain, we can get the change in length. So that's the procedure for doing this type of problem. The other type of problem I could ask you is, a given change in length, an allowable change in length, now find the load that would be required to cause that change in length. And we can solve those problems by taking the change in length and finding the strain, and then using the relationship with the elastic modulus to find the stress. And then once we have the stress, we can find the load or the force required. All right, and remember that the gauge length, that's the original gauge length. That's this dimension right here. That's a constant. And because we're going to use engineering stress, remember from the last video, we're going to use engineering stress, so therefore the cross-sectional area is constant. All right, and this is a review of actually the slides that I went over on the last video, so I won't go over them in detail here, but we're going to do some problems like this. One type of problem is calculate the length change resulting from a given load. So the way we do that is you calculate the modulus, then you calculate the stress. Once you know the stress, you can calculate the strain. And once you know the strain, you can calculate the change in length. I went over that quickly just now, but I went over it in more detail in the previous video. And the other kind of problem that I could ask you is we have a given allowable change in length. What's the load force that's going to cause that change in length? So once again, calculate the modulus first of all. Then you can calculate the strain from these given or knowns. Then you can calculate the stress from these parameters, which are given or known. And then you can calculate the load force from these, which are now given or known. All right, so here's basically what we're going to do. The reason why we want to use intrinsic data like stress and stress-strain curves and elastic modulus is because we can do the tests on one specimen of a given material. This happens to be 6061, which is a real common type of aluminum. So we can do the testing on this specimen of aluminum 6061, and then I can go design a totally different part for a totally different application, and I can use the intrinsic parameters like the ultimate tensile strength, the yield strength, the elastic modulus, and things like that to design my brand new part that looks nothing like this. All right, so that's why we want to use intrinsic data, not extrinsic data that is specific to this specific design, this specific part. I don't actually care about this specific part. I want to use the values of this aluminum, the characteristics, to design some other part that I actually care about. That's the idea. So let's go ahead. Here is our first problem. And in this problem, here is the specimen that underwent testing. And so we put that specimen in the Instron UTM down the hall. And this is the raw data. Notice that this is raw data. You know that because this is the load force and this is the stretch in pounds force, should be pounds force, and inches respectively. So this is not a stress strain curve. Be careful here. Sometimes, I'm not trying to trick you or anything, but sometimes I will give you the raw data and ask you to do calculations on the raw data. And in some problems, I might actually just give you a stress strain curve and ask you questions about the stress strain curve. But this is just raw data. I mean, it's simplified. It only has what, 1, 2, 3, 4, 5 data points, and in your test you're going to get 1,000 or 2,000, a couple thousand data points. So this is simplified, but this is just raw data with load versus stretch. All right, so we're going to use this raw data and the dimensions of this part to answer these questions down here. All right, so question 1 is, what's the effective cross-sectional area? What's the cross-sectional area in inches? Well, the cross-sectional area is, if you took a slice right here, it would look like a circle. It tells you that right here. This is a diameter of 0.375 inches. So what is the cross-sectional area? Well, the way I would do this is if the diameter is 0.375, I would take that divided by 2 to get the radius. And then I would take pi times the radius squared. All right, be careful the order you do that. Don't take pi times the radius and then square it. Take the radius squared and then multiply it times pi. Remember your order of operations. All right, so that is in fact what is shown here. Take the radius divided by 2, then square it, then multiply it times pi, and we get a cross-sectional area of about 0.1104 inches squared. Number 2, what is the gauge length? Oh, this one's nice and easy. There's no calculation required here. this is the gauge length right here. It's the length of the narrow section. And we are generally going to assume, and it's a pretty decent assumption, that all of the stretch is going to happen in that narrow section. Why? I talked about this in last class, but a couple of reasons. Number one, the grips are on the thicker sections here and here, so it's not allowing it to stretch very much. But second of all, and more importantly, because this has a larger cross-sectional area here and here, the stress is much, much lower here and here than it is here. And because the stress is much, much lower, it's not going to stretch as much. So it's a decent assumption, not great, not perfect, but decent. It's a decent assumption to say that all the stretch happens here in the gauge length. So the gauge length is just 1.5 inches. That's nice and easy. And the third question is more challenging. It says, what is the elastic modulus of this material? Okay, elastic modulus is the slope of the elastic region of the stress-strain curve. All right? This is not a stress-strain curve, so be careful here. It looks like this would be the elastic region, but this is the raw data. This is not a stress-strain curve. So what we need to do is think about what this would look like if we converted it into a stress-strain curve. Fortunately, like I showed in the last class session, the shape of the curve is identical. It looks exactly the same. The curve of load versus stretch looks exactly the same shape as a stress-strain curve. The only difference is the values on the axes. All right? So the slope is going to be of this region right here. And if we convert this axis into stress and this axis into strain, then we would have a stress-strain curve, and this would be the linear elastic region of the stress-strain curve. All right, so what we could do, we could, since this looks linear right here, we could select 2 points. We can select this point right here because it looks like that's the yield stress. It will be the yield stress. And the origin, because there's no toe compensation here, so we may as well just go straight down to the origin to make calculations easier. All right, so what we're going to do to find the change in stress divided by the change in strain, well, let's just find what the stress value would be right here at 10,000 pounds force. And since our other point is the origin, we'll just take this stress right here minus 0, because the origin will have 0 stress. That's our numerator, and then our denominator is the change in strain. So let's take this value and convert it to a strain value, and then subtract 0 because it's the origin. The other data point is the origin. All right, so that's what we're going to do. The yield stress here is at 10,000 pounds force. And to get that into stress, we take the force divided by the cross-sectional area. So that's 10,000 pounds force from right here, divided by the cross-sectional area from right here, and we get 90,579 psi. That is the yield stress. Okay? So that's the stress right here. Now, we also want to know what is the strain right here. All right, so the stretch was 0.2 inches. That's the change in length. That's right here. That's the change in length. But strain is the change in length divided by the original length. The original length was right here. It's 1.5 inches. So take that 0.2 inches divided by the original length, which was 1.5 inches, and you get 0.133 inches per inch. So this is the value of the stress at this point right here. And this is the value of the strain at this point right here. Okay? All right, so we're going to select that point, and the other point will be the origin because there's no toe compensation, so why not? It makes my calculation really easy to just subtract 0 from this stress for the numerator, and then subtract 0 from this stress for the denominator. Okay, so that's what we're doing. So the elastic modulus is 90,541 psi minus 0 psi, because 0 psi is the stress at this data point here at the origin. And then we're dividing by the change in strain. Now the strain at this data point was 0.133 inches per inch, and the strain at the origin was 0, so we're subtracting 0. So you can think about a minus 0 right here, just like there'd be a minus 0 right here. Okay. So we just do that calculation, and we get 90,500 psi divided by 0.133 inches per inch, and what you end up with is 680,764 psi. Remember that this is kind of funky. I said this last time, but when we calculate the elastic modulus, the convention is to say that this inches per inch in the denominator, it cancels out. All right. Normally, when you're talking about strain, you still say inches per inch. But when you're calculating the elastic modulus, it's the convention. I didn't make it up. Don't shoot the messenger. But the convention is to drop this value in the denominator and just express the modulus as psi. So that's it. That's the elastic modulus of this material. All right, so we did that test. Now we have a different question. Now the question is, if we applied a 5,000-pound load to this part right here, and notice this is a different part, a different design slightly, but it is different than the part in the previous slide. So if I applied 5,000 pounds force of load to this part right here, what would happen? What would happen? All right, and by that, we're going to mean how much will it stretch. So that's what we're going to calculate, or we'll try, okay? So the important thing, this is what I'm trying to get at here, it's the same material, all right? So this is made of what a metal, and in the previous slide, I'm trying to go back. In the previous slide, this is what a metal, all right? So it's some generic metal. The important thing is that now that we have calculated the yield stress and the elastic modulus in the previous slide for the same material, we can use those values in our subsequent calculations. All right, so we have this new part, so we're going to need to know the new cross-sectional area. That's going to change. So take pi r squared. So take 0.25 divided by 2 to get the radius, square it, and then take it times pi to get your pi r squared. So that's our cross-sectional area now. And our new gauge length is right here. It's 1.25 inches. All right, so the first thing we can do if we apply a 5,000-pound load, well, we can calculate the stress because we know what the load is. So the first logical thing to do, pretty much the only thing you can do, is to go ahead and calculate the stress. So stress is force divided by area. That's 5,000 pounds force from up here. 5,000 pounds force divided by the cross-sectional area, and we get 101,832 psi. Now, it's important to get into the habit of stopping here and comparing it to your yield stress. So this is the stress that's on this part when I apply 5,000 pounds load, and look at what happens. Look at that comparison to the yield stress. So we have applied a load that gives a stress that is higher than the yield stress, and that's a no-no. I mean, whether or not that's above the ultimate tensile strength, I don't know. It might be or it might not be. I'm not sure. I have to go back and we could calculate that, but I'm not interested in that right now. It may or may not break the part, but it's definitely above the yield stress of the material. And so because it's above the yield stress, we stop. And we say, well, I know what the stress is, and I can't determine what's going to happen to the material because I don't have a relationship between stress and strain in that region. You know, I don't have the elastic modulus to give me this nice relationship between stress and strain in the nonlinear plastic deformation region. So you stop and you say that the stress exceeds the yield stress. So our equations are only good for elastic deformation problems, so we can't proceed. We have no way to proceed, so you stop. Okay, so that's not really a trick question, but that is something that I could ask you. I could ask you, what is the elongation of the part if you have this load applied and it turns out that load is above the yield stress? So you can't solve it. So you have to stop and you have to say that we don't have a relationship there, so we can't solve that. So, okay, so we back off a little bit and we say, all right, instead of a 5,000 pound load, let's say we only apply a 4,000 pound load to this same part. This is still the same part. What's going to happen? Well, it's still made out of the material called what a metal. So we still have the same yield stress and elastic modulus that we calculated 2 slides ago. And now our our cross-sectional area, this is the same as the immediately previous slide. It's still 0.049 inches squared. And the gauge length is still 1.25 inches. And we can calculate the stress. The stress is force divided by area. So we have 4,000 pounds force divided by this cross-sectional area, which gives us a stress of 81,466 psi. So this is below the yield stress. So it's going to stretch elastically. We're in the elastic region. So we can proceed. And we can find the change in length of this part because we have a nice relationship, which is the elastic modulus, that gives us the relationship between the stress and the strain. All right, so let's go. Let's go ahead and do it, all right? So we have this relationship for the elastic modulus that says the elastic modulus equals the stress divided by the strain. So what I want to find is what's the strain, because I know what the stress is now, it's this, and I know what the elastic modulus is, it's this, so I can find the strain, and that'll help me work toward finding the change in length. So let's find that. The strain is equal to the stress divided by the elastic modulus. Plug in numbers there, and you get a value of 0.120. Now we can use the definition of strain to say strain is just the change in length divided by the gauge length. And now I know what strain is, it's that. And I know what gauge length is, it's that, which is that. So I can rearrange to solve for the change in length. So the change in length equals the strain times the gauge length. All I did was rearrange this equation right here to find the change in length. So the strain times the gauge length is equal to 0.120 from there, times 1.25 inches from there, and I find that the change in length is 0.15 inches. So if the question was, what's the change in length? The change in length is 0.15 inches. If the question had been, what's the new total length of the part? Well, then we would take the original total length of the part and add the change in length. So the original total length was 4.126 inches. Now the change in length is 0.15 inches, so the new total length is 4.276 inches. Okay, the other type of problem that I could give you is to say we have this part. It's the same part as before, it's the same material as before, and now I'm going to ask what load would cause this part to stretch by 0.1 inches. So before, remember, we said that we've got a 4,000 pound load. How much will it change in length? Now we're saying it's going to change in length by 0.1 inches. What load force is required to make that happen? All right, so we're just kind of reversing the direction that we're solving here. All right, so it's the same part with the same materials, so we still have the same yield stress as before. We still have the same elastic modulus. This is the beauty of using intrinsic data. We still have this same material characteristics that we can use. So we can go ahead and we can say that, well, if it stretches by 0.1 inches, then I can calculate the strain because that is the change in length, and I know the original length. So delta L is 0.1 inches, and the gauge length is 1.25 inches, so the strain is 0.08 inches per inch. Okay, good so far. All right, so next we can use the relationship that is the elastic modulus that it gives us between the stress and the strain. Now we know the elastic modulus from up here. We know the strain, we just calculated it. So now we can rearrange this equation to solve for the stress. So multiply the strain times both sides and you get stress equals elastic modulus times the strain. We know both of these. So plug in for elastic modulus, plug in for the strain, and you get the stress equals 54,461 psi. Now, the first time, remember, the first time in the problem that you find the stress, stop and compare the stress in that problem to the yield stress. Does this exceed the yield stress? Here's the yield stress. No, it doesn't. We're below the yield stress. So good, we can proceed and we can finish the problem. If this had been above the yield stress, then we'd say we can't solve it because we don't have a simple relationship between stress and strain. It doesn't work because we're out of the elastic region. So the only way we can continue is if this value is less than the yield stress, and it is. Okay, so we can solve it. So there's not much left. We can use the definition of stress because we know the value of the stress, and we can say, well, the stress is just equal to the load force divided by the cross-sectional area. And I know, or I can find the cross-sectional area, and now I know the stress from up here. So just rearrange this and solve for the load force. So multiply this equation, both sides, times the cross-sectional area, and you get the load equals the stress times the cross-sectional area, which is 54,461 pounds per square inch times 0.0491 inches squared. So you got inches squared in the numerator, inches squared in the denominator, they cancel out, and you're left with just pounds force in the numerator. And you get 2,674 pounds force. So that's the force that if you applied to that specimen, it would result in a change in length of 0.1 inches. All right, so recap of what you should do with these types of problems. We're going to use the test specimen to get the intrinsic data from this material. And then we're going to convert to stress and strain by using the cross-sectional area and the gauge length of the part. We're going to need to find the yield stress, and we're going to need to know the elastic modulus for pretty much all of these types of problems. And then you're going to use those three equations for stress, for strain, and for elastic modulus. Rearranging those equations in various ways is going to allow us to solve for whatever we're trying to get to. So it just takes some practice. When you first do these problems, it's going to take a little while. You're going to have to think at every step, okay, what do I know and what can I find next? It's going to take you a little while to kind of get comfortable doing these problems. But if you do a bunch of them, then you will start to get comfortable and it will start going a lot faster. And remember, the first time you calculate the stress in the part, as you're doing one of these problems, stop, compare it to the yield stress. If it's above the yield stress, stop the problem. You can't solve it. Okay, in the next section of this video, I'm going to go to page 37 of the lab manual, and we're going to solve the questions on page 37 in the lab manual. So what I really highly recommend you do before proceeding is pause the video and try to solve these questions on page 37 by yourself. If you just watch the video and you watch me do it, I promise you, you will not learn as much as if you do it yourself. And if you just follow along with me and, kind of say, all right, that makes sense, that makes sense, that makes sense, then you're going to have a much harder time when it comes to the quizzes and the exams, and they're going to feel much harder than if you just challenge yourself now. Challenge yourself to do the difficult calculation work right now, and it's better to struggle right now than it is to struggle on the exam or the quiz. So take a little bit of time and try to solve these questions on page 37, and then we will go over them together. Okay, we're on page 37 of the lab manual now, and I would strongly recommend that you try to solve these problems yourself first, but I will go ahead and assume that you have done that. So let's solve these. The first question on page 37 gives us a stress-strain curve now. So now it's not just the raw data. This is stress in PSI, and this is strain in inches per inch. And the first question is, what is the modulus of elasticity for 2011? So this is aluminum 2011. That's the kind of aluminum, that's the material that was tested here. So we just want to know what's the modulus of elasticity. Remember, the modulus of elasticity is the slope of the linear elastic region of the stress-strain curve. That linear elastic region is this region right here. And notice on this curve, it looks like there was quite a lot of toe compensation right here. Remember, we talked about how that's caused by slop in the fixture. And when you start the test, first you pull out the slack in the fixture. So that's why you get a bunch of strain without much stress at all. And then you start taking a force on the specimen. So then you actually start the test. So we don't want to use the origin here as one of our parts, or one of our points, because that would give us a very incorrect slope. Then our slope would look like that, whereas really our slope looks like this, right? So you can't use the origin here as one of your points. It won't work out. So the 2 points I'm going to use, I'm going to try to make them as convenient as possible. I'm going to use this point here at 50,000 psi of stress, and then I'll draw a dashed line here, and I'm going to say, what did I say? I said that this is a strain value of 0.043. That's my best guess here. And my other point is right here at 10,000 psi. And I'm going to assume that this strain value is equal to 0.024. That's my best guess right there, just kind of interpolating between these data points. All right, so basically I've got this point and I've got this point. I'm going to take the change in stress, that's 50,000 psi minus 10,000 psi, and I'm going to divide that by the change in strain, and the change in strain is 0.043 inches per inch minus 0.024 inches per inch. And when I do that, and I solve that equation there, I find that the modulus of elasticity is a little over 2.1 million psi. Your value is going to be a little bit different depending on what points you picked up here and what numbers you assumed, but it should be pretty close, probably within about 10%, I'd say, of that. If you're within 10%, that's probably pretty good. The next part, what would happen if a 10,000 pound load was applied to the specimen on the right? So that's this specimen over here. We know what the diameter of the gauge section is, and we know what the gauge length is right there. What would happen? So, well, the only thing we can really do here, we have the force or the load, so we can calculate the stress. And the stress is force divided by area. So what's the area here? Well, it is 0.25 inches divided by 2, which is 0.125 inches squared times pi. So your cross-sectional area here is 0.0491 inches squared. Now we want to calculate the stress. So stress is force divided by area. We have a 10,000 pounds force divided by our cross-sectional area, and that gives us a stress of 203,720 psi. Now compare that value to our stress strain curve. We had 203,000. That is way, way above even the ultimate tensile strength right here, wherever this is. You know what, that's 56 or 57,000 psi. Anyway, this stress is way above the yield and the ultimate tensile strength. So I wrote, it would exceed the yield strength and the ultimate tensile strength, so it would break or fail. It's definitely true. It would definitely break or fail since it's way above the ultimate tensile strength. Part C says, all right, back off from the 10,000 pound load. Let's say a 1,000 pound load was applied to the product. How much would it stretch? All right, so once again, you start with what you can. The only thing you can really start out with here is the stress. So you have the force and you know the cross-sectional area, so you can calculate the stress. So the stress is the force divided by area. That's 1,000 pounds force divided by our cross-sectional area that we calculated before. And that gives us 20,372 psi. Now even that number, we check it. Go up here to the stress strain curve, about 20,000 psi. So we're about here on the stress strain curve. So now we're good. That's good because that's definitely in the elastic region of the stress strain curve. So we can continue. All right, so eventually we're going to want to get to how much it's going to stretch, and that's related to strain. So what I'm going to do is rearrange the elastic modulus equation to solve for the strain. So here's our equation for elastic modulus. I'm going to rearrange and solve for the strain. So now the strain is equal to the stress divided by the elastic modulus, which I know. And I also know the stress, so plug in the stress value from here, plug in the elastic modulus value from part A, and you get a strain value of 0.00968 inches per inch. And now the last thing is, I know the strain, I know the original length, so I can use the definition of strain to find the change in length. So there's the definition of strain. Now I'm going to rearrange and solve for the change in length. Change in length is equal to strain times the original length. Plug in numbers there. There's the strain that I just calculated. There's the original length from the drawing. Plug in numbers, cancel out units, and you get 0.012 inches for an answer. That's how much it would change in length if you applied 1,000 pounds load. Okay, that's page 1, and then we go to the next page. Now we have a new connector. This is a different part, all right? So we have a different part here. I'm just trying to cover up part of it so that you don't get too confused by looking at it. So we've got this part, and we got a 5,000 pound load. And it's made of the same material, so we can use the same elastic modulus and the same yield stress. How much will it stretch? All right, so this is pretty much the exact same problem that we just did, but it's just going to have a different cross-sectional area, and it's got different values because it has a different force here. All right, so we need to know the cross-sectional area. So that's 0.375 inches divided by 2, and then square it. Take it times pi. So that's 0.1104 inches squared. And now we get the stress. The stress is force divided by area. 5,000 pounds force divided by 0.1104 inches squared. And we get 45,290 psi. Go back and check this number on your stress strain curve and make sure that's in the elastic region. Here it was, and it's about 45,000. So that's about right there. So we're definitely still in the elastic region, so we're still good. We can still proceed. All right, so we're going to want to get to stretch, which is change in length. But to get there, we're going to need to know the strain. We now know the stress, and we already know the elastic modulus, so we can use the definition of the elastic modulus to get to the strain, just like in the very last problem we just did. So rearrange this equation to find the strain. Strain is the stress divided by the elastic modulus. Plug in values here, and you get that the strain is equal to 0.0215 inches per inch. And lastly, now that we know the strain and we already knew the original length, it's 1.5 inches from the drawing right here, we can solve for the change in length. So here's our definition of strain. Rearrange and solve for the change in length. Change in length equals the strain times the original length, and you plug in values. The strain we just solved for was 0.0215 inches per inch. The original length was 1.5 inches, and our final answer, therefore, units cancel out, and we get 0.032 inches. Excuse me. All right, then the next problem is a different kind of problem. The question is, what is the load, force, that will be needed to cause it to stretch by 0.01 inches? So now this is the backwards version of the previous problem. Now we know the change in length, and we want to work backwards to find the force that is required. All right, it's still the same material, so we still have the same parameters. All right, so the first thing we're going to do, since we know the change in length and we know the original length, let's solve for the strain. The strain is the change in length, that's 0.01 inches. The original length is 1.5 inches, so the strain is 0.0067 inches per inch. Now we know the strain, and we also know the elastic modulus, so we can use that relationship to find the stress. So rearrange the definition of the elastic modulus to find the stress. Plug in your values for the strain that we just calculated and the elastic modulus that we calculated earlier, and you find that the stress is 14,035 psi. Now, once again, take that number and compare that to the stress strain curve, 14,000 psi, and we're somewhere about right there on the stress strain curve. So we're definitely still in the elastic region, so we can carry on. So we're at 14,000 psi, and we want to know how much force does that equate to. So we have an equation that relates force and stress. Here's our stress equation. Rearrange and solve for the force. Force equals stress times area. Plug in the value for the stress that you just calculated. Plug in the value for the cross-sectional area that you already have from the previous problem. And you find that your stress is, the force is equal to 1,550 pounds force. So that's our final answer to that problem. And the last problem here is, what load will cause the new connector to reach yield stress? All right, so this one's actually even a little bit easier because we know what the yield stress is by looking at the plot. So let's look at that. The yield stress was about 52,000. What did I say? Yeah, about 52,000. That's what I said. So 52,000 is about the yield stress. So we want to know what force will cause a stress of 52,000 psi. So this is pretty simple, actually. We just have a relationship between stress and force and area. Rearrange this equation to solve for the force. Plug in your values for stress and area here and here. That's our yield stress, and that's our cross-sectional area that we calculated previously. And your units cancel out, and you get a force of 5,741 pounds force.
All right, that's going to wrap things up for this video. I would make sure that you're real comfortable solving problems like this on page 37 and 38 and on the slides that we talked about earlier in this video. These are definitely the types of problems that you will see coming up on exams or on quizzes in the near future. So make sure that you're comfortable with that. If you have any questions on that, by all means, get in touch with me, send me an email or contact me by phone, or come to my office hours. That's probably the best option, honestly. Or we can talk during the lab sessions or after one of the lab sessions. So make sure that you're real confident solving these different types of problems that we just talked about. All right, so that's going to be it. I look forward to seeing you in the labs, and have a good week.